So today we are discussing about the question on the GFG, that is diameter of the binary tree. So what is the meaning of the diameter of the binary tree? It is there is a given a binary tree. The diameter, also known as a width, is defined as the number of edges on the longest path between the two leaf nodes in the tree. This path may not pass through the root, and your task is to find the diameter of the tree. Okay, we can take this example. What is the diameter of the tree as the number of edges, the longest path between the two leaf nodes is the diameter of the tree. So there is one leaf node, there is second leaf node, 2 and 3 is the leaf node. The longest part within this two leaf nodes is uh, using edges, this one edge, the second edge. So there is the longest part between these two is using these two edges. So the answer to this, the diameter of this tree is 2. This is 2. And let's take another example. In this, there is a leaf nodes 3, 7, 9. We can identify the leaf nodes, and we can take that 3 and 7 are the leaf nodes. The distance between them is the one edge 3 to 8 and second edge 8 to 7. There's two edges. So the distance between 3 and 7 is 2. Now we check for 3 and 9. 3, 3 to 8, 8 to 5, 5 to 6, and 6 to 9. There is a 4 edges in between them. So there is a 4 distance in between them. So this is the up to now there is a 4 distance from 7 to 8 and 8 to 5 and 5 to 6 and 6 to 9. There is also 4. So the answer to this is the diameter is longest is 4. So and uh, and this is the test cases we have given, and the one thing is that thing that is happening is that this path may or may not be passed through the root. It is not necessary to the path will be passed through this root. This the path is the longest diameter should be in here. There is more roots, and there is a longest path in longest diameter in left part, either in the right part we can find the longest diameter. So from the from our thinking we can think of that, using a recursion we can find that this is the root. We can search our diameter, longest diameter, in left part and right part, and take the maximum of that diameter, and we can find the maximum diameter of the tree. But how can we do, and how can we achieve this? So any node, at let's say we can start at how can we achieve the diameter of that node? Yep. So we can take a height of this, because there is a height. This is one height, there is a one height here, there one and one two height. So the diameter of this is the max height of this, and sum of both of them height. There is a diameter of that 8. So on we can do, and let's more clear with the code. We can see the recursive code first, and this then afterward we can see the optimized code. And in this, let's say the diameter we have to calculate. So if the best case, there is a best case, if the root is null, so we can return 0. There is a no diameter, no longest diameter of that. So int x, we can find the diameter. I can say that we can find the left and right. So we can call the root left and root right of that tree, and after that we can also calculate the height of the diameter of the tree. So how can we calculate the diameter of the tree? Is that using height of the tree? We can discussing that at we can find it max height of this, max height of here, then add on them, then we can max of height of root left and root right, and this will be give us the diameter of that node. Oh, and after finding this we can max return max of that left, right, and current nodes is diameter. So how to find a height of that? This is also can be find using recursion. If the root is null, then return 0 and x. And in this we can left call, right call, and max of that left and right calls, and add 1 to it. There is a one edge with this left call and right call, right root left. This 8, we can call out 3, we can call out 7. Suppose the 8 will be go here, root is 8. If the then the root left is 3 and root right is 7. So this edge between 3 to 8 and 8 to 7 will be added using this 1. Okay, either the left will be maximum, either the right will be maximum, so we can add only one edge. So this will be give us the height of that uh, binary, and that's all. We can find our answer using the recursion. And now we are discussing the optimized version, because this is the taking a time complexity of big of n square and two recursive stacks. That's also big of 2n. Okay, so we are now discussing about there is optimized code. So we can make a two calls at a time, and we can observe that the codes are similar for diameter and height. That's making a root, a left call, right call. The calculation is different. The calculation for this is maximum of x comma y plus 1, and calculation of this is height of root and height of left. So we can optimize using the pair comma int ले लिए हमने, and in this solo function, if root is equal to null, we can return 0. The diameter first pair is for the um, first pair is for the height of the tree, and second pair is for the diameter of the tree. The height and the diameter of the tree. So height and diameter. X is equals to solve root left. In same we can do here. Left call, the right call, then we can take a height. So we can store a height in the first. So we can store our height left and height right into the HL and HR variables, and diameter left and diameter right into the x dot second, y dot second. And for we know that there is a only difference in between these codes are that this calculation part for the height and that diameter, then this calculation part and we can differ. So we can here mentioning there max of HL and HR left and right heights and plus 1, and DL max of DL, that's diameter left, max of DER, that's diameter of right, and HL plus HR we can do is here is also that's height of root left and height of root right. So this is height of left and height of right, and this will be written answer, and this will give us the a pair comma int, there is a height and there is a diameter. So we can take our written diameter as a answer, and it is very there is a this code having a time complexity of big O, and there is a n is the total nodes in our binary tree, and that's all.